Okay, so this video is just going to go over the Bohr model exercise that you all did as a in-class / take-home exercise, depending on how our timing was. So here are the 4 assumptions that went into Bohr's derivation of the energy levels for a hydrogen atom. And we are going to just work through the exercises from this handout. Okay, so first question asks us what Z represents in our model that was described above. So where we have a nuclear charge of plus ZE and a mass m, electron mass of little m, and charge of minus E. So in this case, Z is representing our atomic number. Okay, also known as your number of protons. Okay, so obviously for a hydrogen atom, Z is inconsequential, so whenever you see equations that are dealing exclusively with the hydrogen atom, you're not going to see a Z incorporated into any of those equations, but here we are trying to expand the model to be useful for any general one electron system. Okay, so this way we'll be able to use these equations to model helium plus, lithium 2 plus, so on and so forth, so any one electron system. The next question asks us to write an expression equating the classical force equation for motion in a circle and the magnitude of the Coulombic force expression between 2 charged particles. Okay, so here we are remembering back to our physics. So our equation for motion in a circle, mv squared over r, and we want to equate that to our Coulombic force between 2 charged particles. In this case, our charges are Ze and E, and our denominator 4 pi epsilon naught r squared. Okay, and next question is asking us to use the above equation along with Bohr's 4th postulate, which was the quantization of angular momentum, to derive an expression for the radius of an electron in terms of h bar, according to the Bohr model. Now, you'll see this equation given in terms of h bar. Okay, we just want to be consistent for everyone, so I've specified h bar for this particular exercise. So let's start with our equation from number 2. And we know Bohr's 4th postulate, where we have mv r, our angular momentum, being quantized. So we know that equals nh over 2 pi. And we want things in terms of h bar, so we'll just convert that to n h bar. So remember, h bar equals h over 2 pi, and we call that our reduced Planck from Planck's constant. Okay, so let's take this equation and solve for v squared, or v first, and then we can square it. So nh bar over mr gives us v squared of n squared h bar squared over m squared r squared. Okay, and then we will just plug that further into our equation from up above from equation 2 up here. So we're going to plug it into this mv squared over r. So that leaves us with m n squared h bar squared over m squared r cubed. So we have that r squared and then the r in the denominator from up above. Give us r cubed. And then, remember, we still have our Coulombic expression over here. Okay, so now our job is to solve for the radius. Okay, so when we take a look at our expression, we can cancel a couple of things right off the bat to simplify our lives a little bit. So those m's cancel, the r's cancel, so we're left with just m times r on that first denominator, and then now we can just rearrange to solve for r. So this is where your crucial algebraic rearrangement skills, your math skills, are going to come into play. So once you do that magic rearrangement, you should end up with 4 pi epsilon naught n squared h bar squared over z e squared times m. Now remember, these masses and velocities are particular to our electron, so we could denote those with little subscript e's to remind us that we're dealing with our electron in this system. Okay, so there we have our expression for the radius of an electron according to our Bohr model. So now we see that we have that z factor in there. So again, this will work for any one electron system. So you just have to account for your atomic number in that denominator. Okay, so question 4 is asking us to calculate the radius for the lowest energy state, also known as our ground state, for n equals 1. So remember, your integers there, those n values, can take on any value from 1 all the way up to infinity. For this particular case, there is no n equals 0 allowed, and we will talk about that later when we solve the Schrodinger equation for this system. But for now, we'll just take it at face value that n equals 1 is our lowest possible energy value, or energy state. So we want to actually calculate the value for this radius in units of meters and angstroms. Okay, so we have a bunch of constants here, so just plug those into your calculator. So we have a mass of our electron here, 9.11 times 10 to the minus 31 kilograms. That epsilon naught, this is our permittivity of free space, 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Elementary charge E, 1.602 times 10 to the minus 19 coulombs. And for our ground state, we have n equals 1. So those values you can look up. Macquarie has a table of all these physical constants in the front cover. You can find them on Wikipedia or your favorite reference source. So plug those values into your handy-dandy calculator, and if life is good to you, you should get a value of 0.529 angstroms. Also known as 0.529 times 10 to the minus 10 meters. Alright, so you probably got the meters first, but remember 1 angstrom is equal to 10 to the minus 10 meters. Okay, this is a very important unit for chemists to be familiar with, the angstrom. You'll see that pop up quite a bit in your life as a chemist, particularly when we're talking about things on the order of bond distances. Okay, so we will see angstroms again, so you can commit that conversion to memory and make life easy for you. Okay, so radius of the ground state of a hydrogen atom, or a one electron system, we should say, is 0.529 angstroms. That is known as the Bohr radius. Okay, so you'll see that value referenced later on in the semester. Okay, that's going to have the value of A naught. So whenever you see A naught, that's the symbol for Bohr radius, and you know now that that is equal to 0.529 angstroms. Okay, so now we're on to using the classical expression for total energy and the expression for the Bohr radius we just got to show how we end up with the following result for the energy for an arbitrary stationary state in our system. Okay, so let's start with our classical expression. So we know that our total energy is the sum of our kinetic energy, 1/2 mv squared, and our coulombic potential energy that we've seen before, Ze squared over 4 pi epsilon naught r. Okay, so one thing to point out here is, where did this minus sign come from? Why aren't we adding them together? Well, we are, but remember our potential energy U here is an attractive force, so it gets a negative sign for us. Okay, so just be careful there. You might have an issue with your signs first time through this. Okay, so there's our classical expression for the total energy, and we're going to couple that with our expression for our Bohr radius that we have from before. Okay, now we're going to do some subbing here. Let's also remind ourselves for our velocity squared. Remember we used this earlier. Okay, so now we do fun with substitution. Okay, so our equation for our radius, we can pop that in there, and also right there. And then our equation for velocity can get popped in right there. So just substituting these lovely equations in there, we should be able to end up with something that works out for us. Okay, so I'm going to let you do some practice with that substitution in there. When all is said and done, if you do your accounting correctly, you should end up with something along the lines of this equation. Okay, so lovely. Remember, that's mass of an electron. We'll just match it up with our expression above. Okay, so close but not quite there, because the expression that we're asked to obtain is in terms of H, not H bar. Tricky, tricky. Okay, so you just do your substitution in for H bar. Remember our conversion, H bar equals H over 2 pi. Don't forget that your H bar here is squared. Okay, be careful on that. All right, so sub that in, do some cancellation, and you should get our expression that we want. As such. Perfect. All right. So here we'll just be consistent and add our little e's next to our m's for consistency. Okay, so there you go. So this one is all about substitution and making sure that you do your canceling and accounting correctly to end up in the right spot. So here we have our energy level expression for a 1-electron system. So we could use this expression to calculate the energy levels for any 1-electron system that we may be interested in. So that little subscript n just denotes that that's the energy for a particular energy state, whatever that may be. So if you want the ground state energy, you would write E sub 1 to represent your n equals 1 energy state. All right, so here we are tasked with showing explicitly that the expression we just obtained has units of energy or joules. Okay, so now we're just going to look at our units and see how they work out. All right, so units on Z, no units, nice and easy. Units on our elementary charge, we know from before those are coulombs, so we'll get coulombs to the 4th power. Units on our mass, we get kilograms, and that's it for our numerator. If we look down below, units on our permittivity of free space, epsilon naught, are coulombs squared per Newton meter squared. But then that is squared. Okay, and then n has no units, and we're left with our Planck's constant, which we know has units of kilogram meter squared per second. But be careful, that critter is also squared. Okay, so at this point, we're looking pretty good, except for this little Newton down here isn't really working out for us. So when in doubt, if a unit's not working out, check and see if there's alternative units you can use. So turns out a Newton, and you can probably make this deduction based on our alternative units that we saw before for or Planck's constant in the de Broglie exercise, a Newton is also equal to a kilogram meter per second squared. So I like those units a lot better for this. All right, so if we sub those in there, get everything multiplied out, gonna have coulombs to the fourth over kilograms squared, meter squared, per second to the fourth, which is the same as bringing it up here. Try that. And then we have our kilogram squared, meters to the fourth over second squared. This is fun. Okay, so let's do some canceling. All right, those guys cancel. These ones cancel. Meters are going to cancel. We'll be left with 2 there. Those will cancel, left with 2 there. All right. I think that's it. Okay, so we're left with kilograms and where did I go wrong? Okay, so I can see these aren't working out, so let's go back and double check that we got everything brought over, and oh, I see it. I think I missed carrying over that meter squared right there. So I subbed in the kilogram meter per second squared here for the Newton, but I forgot my m squared, which I need to square. So we'll just fix that. See, it's okay. If things don't work out right away, you can find your mistake. You just gotta go back and take a look-see. Okay, so that means we want, I'll make this a different color so we can see what I'm adding. So we need a meter to the fourth down here. That's still hanging out. Okay, so then, remember that's coming from that guy. Okay, so let's keep going. So we have meter to the fourth down here, meter squared, so that one's going to go away. And we're still left with 2 down there. So now we have kilograms per second squared per meter squared, so we can bring those meters up top, and then we have per second squared, and I think that is where we want to end up. Yep. 1 joule equals kilogram meter squared per second squared. We are in business. All right, there you go. So, lots of units, lots of fun stuff. So just be careful. Make sure that you remember to square everything inside those parentheses. Do your substitution for your newtons. And then be careful with your canceling. And then remember your tricks for fractional denominators, right, where you can bring these denominators in the denominator up to the top. All right, looks good. Moving on. Actually, not moving on because I think that was our last question. Okay, cool. Well, hopefully that helps you to catch any mistakes you might have made when you were going through this exercise, or shows you some extra tricks that might come in handy down the road. So key here is remember that there are alternative units for just about everything. So if the unit that you're working with isn't useful to you, just go look and see if there are other ones that might be more appropriate for your particular task and application. And you just got to be careful with your accounting of everything. So mistakes happen. The skill is in being able to go back and find where you went wrong. All right, so hopefully you found that helpful, and that'll do it.